Is it on?
Yep.
Okay, this video is on Dyck Words. It's named after a German mathematician, Walter von Dyck. So the definition of a Dyck word is something that has balanced parentheses. So a simple one, for example, is that, or that's a Dyck word of length 1 because it has one set of balanced parentheses. These are Dyck words of length 2. So this is 1, this is 2. And then of length 3, they look like this. So in other words, the parentheses are balanced. And so on. This isn't very clear. Yes, that's 1. And then finally, I'm missing one. There's 5 of length 3. So anyways, the number of Dyck words of length n is the nth Catalan number. And this has a very interesting recursive relation, which is the sum from I equals 0 to n minus 1 of ci times c n minus 1 minus I. So it turns out this is just equal to 1 over n plus 1, 2n choose n. And if you use Stirling's approximation, this is approximately 4 to the n over n to the 3 halves times the square root of pi. So the number of Dyck words grows exponentially with n. So that's a little taste of how Dyck words work, and hopefully you can come up with some examples in the comments. I'm looking forward to see what you come up with. Thank you very much. Given that last expression for the number of Dyck words, we can see using Stirling's approximation that there are infinitely many Dyck words. So I thought, I wondered if I could write a computer program that would generate Dyck words. So I was playing with it using like string concatenation and stuff, and it was really hard. Then I realized this tree interpretation is the easiest way to do it. So every node in the tree is either an open parenthesis or a closed parenthesis, and then the branch to the left is an open parenthesis, and the branch to the right is a closed parenthesis. And there's certain rules, like you can't have more closed parentheses than open parentheses. So for the Dyck words of length 1, we just get this tree. For the Dyck words of length 2, we get this tree. And you trace the path from the root all the way down to the leaf, and that path gives you the Dyck words. So if we trace this path, we get this one here on the left. If we trace this path, we get this one here on the right. So if you think about that recursively, it's a really simple algorithm. You just keep track of the prefix, and then every node is either a left parenthesis or a right parenthesis, and then you just recursively create a tree to the left or to the right. So let me show you what that Python code looks like. So here's the Python code that implements that. So I'm implementing a class Dyck words, the Dyck words of length n. This data is either an open parenthesis or a closed parenthesis, and then we keep track. How many open parentheses do we have and how many closed parentheses do we have? Because we need that in the recursive construction, because we want to make sure we stop at the right level. So we have a left tree and a right tree, and the data, this is the open parenthesis or closed parenthesis. So at the nth level, we can have at most n open parentheses. So if n is less than, if the number of open parentheses is less than n, then we can keep going. So we create the left subtree that has the open parenthesis as the data, and we have one more open parentheses, and we make this recursive call. And similarly, for the right half of the tree, we need the number of closed parentheses to be less than the number of open parentheses, and then we recursively make a call for the right-hand side with one more closed parenthesis. And that's it. This is the construction of the tree. Now, if we wanted to print the Dyck words, we just walk down the tree and only print the leaves of the tree. So if you have a left node, just recursively go, but add a open parenthesis to the prefix. If you have a right tree, make a recursive call and add a closed parenthesis. And then finally, this, if you have no left child and no right child, then you're at a leaf, so you just print the prefix. So we're just printing down the paths of the tree. And it's just that simple. And if we wanted to count the Dyck words, we just say if you have a left tree, count left. If you have a right tree, count right. If you're a leaf, you just have one Dyck word, and then you just return the answer for the recursive case. And that's all there is to it. So I'll print the first 10 Dyck words and then print the trees. Okay, so I'm first printing the number of Dyck words. So, like, of 10 sets of open and closed parentheses, there's 16,796 Dyck words. And then I'm actually walking the tree and printing them out. So here's the Dyck word with one set of parentheses. With two sets of parentheses, we get this. With three sets of parentheses, we get this, and so on. So I wrote a computer program to generate Dyck words, and the cool thing is that there's an infinite number of Dyck words. So with a little bit of recursion, we were able to trivially generate Dyck words, and so I'm curious to see what kind of Dyck words you guys can come up with. Thank you very much.